Today we are going to start constant velocity. We'll be working on this unit for the next few weeks, and I figured this would be a great way to introduce it. I'm going to start with 6 definitions, and then I will do an example. If you would like to see more examples aside from the one that I'm going to show you, I will make a separate video with some more examples. What you should pay attention to are the definitions, any equations, and then of course the example. So make sure you take good notes and have them ready for class tomorrow. Our first definition is a scalar. A scalar is a quantity that only has magnitude. So magnitude just means amount, it's a number. In other words, a scalar is going to tell you how much of something there is. It can only be positive. You can't have negative quantities of anything. Examples of scalars would be time, distance, and speed. And one easy way to remember that time is a scalar, time can never go backwards, therefore time can never be negative. Next we have a vector. A vector is a quantity that has a magnitude and direction. So it's going to tell you how much and what way the object is moving, or what way a force is acting, what way it ends up, what way an object ends up. Because it has direction, a vector can be positive or negative. Negative just means that it's moving to the left or down. Positive refers to anything going up or to the right. Examples of vectors would be displacement, velocity, acceleration, or force. Our next definition is distance. Distance is the total path length an object travels. In other words, it's how far you went. It can only be positive. You can't have negative distances. So for example, if you're driving, your car has an odometer. That odometer tells you how many miles your car has. That number is only going to be positive. That number cannot go backwards. It tells you the total amount of miles. So distance is the total amount that you travel. The symbol is just an X, and the units can be miles, kilometers, meters, etc. So anything that's a unit of length would be a unit for distance. The most common unit that we'll use will be meters. Our vector version of distance would be displacement. So distance is a scalar. It can only be positive. It's just telling you an amount. Displacement is the vector because it has to take into consideration direction. Displacement is the change in position of an object. So it's its final position minus initial position, or where it ends up in relation to where it started. Displacement can be positive or negative. That means, once again, if it ends up to the left or below where it started, it's negative. To the right or above would be positive. Since displacement is a change, the symbol for displacement would be delta x. And you should recognize the delta from math class. Delta, again, just referring to change. Units for displacement are the same as the units for distance, meters, kilometers, miles, etc. And the equation for displacement is right in the definition. Delta x equals final position minus initial position. Okay, we're to our last 2 definitions. The second to last one is speed. Speed is the distance traveled in a given amount of time. Speed can only be positive, therefore speed is a scalar. It's just telling you how fast an object is moving. An easy way to remember that speed is a scalar, they both begin with the letter S. The symbol for speed is a script V, so it's a V with a little hook on it. I'm not going to be super picky about the symbols that you use. It's just a V. Units for speed, most common ones that we'll be using are meters per second. Other units you might see, kilometers per hour, miles per hour, etc. Pretty much anything that's a unit of length over a unit of time. The equation for speed is in the definition. Speed is equal to distance over time. And whenever I write equations, I like to define what each letter is. So x is distance, t is time, and v is speed. And our last definition is velocity. Velocity is the displacement of an object in a given amount of time. It can be positive or negative because velocity is a vector. An easy way to remember that velocity is a vector, v. They both begin with v. So speed is a scalar, velocity is a vector. Velocity is not only going to tell you how fast something moves, it's also going to tell you which way. Is it moving to the left? Is it moving to the right? Is it moving up? Is it moving down? The symbol for velocity is a v without the hook. Again, I'm not going to be picky about the symbol. Units, same as the units for speed. Meters per second, kilometers per hour, miles per hour, etc. The equation for velocity is in the definition v equals delta x over t. Where delta x is displacement, t is time, and v is velocity. Now, when does it make sense to use speed versus velocity? You want to use speed if you're changing your direction to get a pretty accurate idea of what your average speed would be, since speed will tell you how far you went in a given amount of time. Velocity will make a little bit more sense to use if you're traveling in the same direction the whole time. So if you're going to the left at a certain, speed, that'll give you an accurate representation of your velocity. If you change directions, and you'll see in the example, velocity might not make the most sense. Okay, let's do an example. Heather walks 5 meters to the left at a constant velocity, then turns around and walks 3 meters to the right at the same rate. If it takes her 20 seconds total, determine her distance, displacement, speed, and velocity. We know that distance is the total amount of path that she travels, so her distance will simply equal 5 meters plus 3 meters, meaning she traveled a total of 8 meters. So distance equals 8 meters. For her displacement is her change in position, where she ended up versus where she started, or final position minus initial position. So delta x would equal 3 meters minus 5 meters, equaling negative 2 meters. Negative because she ends up to the left of where she started. So displacement equals negative 2 meters. Next thing it asks for is her speed. So how fast was she going the whole time? Speed equals your total distance divided by the time. So this equals 8 meters divided by 20 seconds. 8 divided by 20 is equal to 0.4 meters per second. Her speed gives us absolutely no indication of which way she was moving, it's just telling us how fast. And the final thing the problem asks for is her velocity. Velocity is equal to her displacement over the time, so this equals negative 2 meters divided by 20 seconds. Negative 2 divided by 20 equals negative 0.1 meters per second, so her velocity equals negative 0.1 meters per second. This is telling us that her average velocity for her entire trip was to the left and negative 0.1. In this case, the speed is going to be a little bit more accurate because her direction changed. Had her direction remained the same the entire time, the velocity would have given us a more accurate representation. And just to kind of further that thought, let's say Heather started and ended in the same place. So let's say Heather walks 5 meters to the left and then she turned around and walked 5 meters to the right. Her final position minus her initial position, in other words, her displacement, would be 5 meters minus 5 meters, or 0 meters. If you start and end in the same spot, you have no change in position, therefore your displacement is equal to 0. If you have a displacement equal to 0 meters, and velocity is displacement over time, your velocity would be 0 meters over the 20 seconds it might have taken her. So a displacement of 0 meters would mean a velocity of 0 meters per second. This is only true if you start and end in the same place. Displacement and your average velocity would both be 0. And you can see why it would make sense to look at your average speed for a more accurate representation of how fast she was going. If this makes sense to you, you don't need to see any more examples. Just come to class tomorrow ready to work on a few problems. If you would like to see some more examples, I will do 2 more in another video.